Hello, this is Happy Potato speaking, and this is not procrastination. This is part 1 of the first section of the Edexcel IGCSE Physics Syllabus called Forces and Motion. From this section and for all physics in general, we need to know a few basic units. For example, we need to know kilograms, meters, meters per second squared, newtons, and seconds. And we also need to know newtons per kilogram and kilogram meters per second, but that will come later on, all of which can be written down in shorthand. We have kilograms as kg, meters as m, meters per second as ms, meters per second squared ms squared, n and s for newtons and seconds respectively. Don't worry if you've never seen them combined before like that and you're not sure what they mean. We'll go through them in a lot more detail later on. Alright, first things first, distance time graphs. Now, let's say we had a, let's get you in this shot. Yeah, there you go. That's a bit, are you gonna get out of the way now? Okay, right. So, let us say that we have a cat moving through space. And this cat is moving away from the planet Zargon. If we drew a distance time graph, of the movement of the cat from the planet Zargon, and let's say it looks something like this, the distance is increasing as the time increases, so the cat is getting further and further away from the planet Zargon. So if this was a perfect graph, that is a gradient that is definitely positive, and that is what it looks like with a speed that is constant, since the gradient of the graph is constant. What if we have it in the other direction and we have the distance decreases as time increases? What that means is the cat is getting closer to the planet Zargon because she's rushing home because she forgot her lunch as she was speeding away for the galactic interchange. Now, since that's all perfectly logical, what would it mean if the gradient of the graph was 0? What if the line was flat? Well, that would mean that the distance between the cat and the planet Zargon isn't changing. This distance is constant. And therefore, the cat is staying still. So this arrow can disappear. Now, it seems straightforward, doesn't it? And it is, really. There isn't that much more that we need to add on to the gradient of a distance time graph. So basically, as you can see here, the gradient of a distance time graph is the speed of the object. So if we have one that's a bit wonky that changes over time, so it looks something like this. Since the x-axis is time and the y-axis is distance, if we do distance over time, if we divide the y-axis values by the x-axis values, or if we just want to find out how fast the cat is moving at some point in time, all we have to do is divide the distance value by the time value to get the speed. Why, you ask? Well, if you can remember correctly, which I'm sure you do, speed is measured in meters per second. And that's exactly what we get when we divide the distance by the time. So if we want to find the speed of the cat at this point, we would only need to divide this value, which is, let's say, 10, by this value, which is, let's say, 5, in which case we would get a nice clean 2 meters per second. Right. This is going to be very handy in exams and in general in life, so make sure you understand why the gradient of the graph is speed rather than just memorizing. If you're having trouble figuring out the distance time graphs, don't be scared to just pause and rewind the video until it makes sense before you move on. Right, an important equation which illustrates something we just proved we understood is the equation average speed equals distance traveled over time taken. Why is it average speed and not speed, you ask? Well, if we go back to our kitty from the planet Zargon, there's our kitty again from planet Zargon, who seems to be losing weight. There's our planet Zargon. Well, we can see that the speed, which is the gradient of the distance time graph, isn't always constant. It can be variable, it can be changing. It doesn't always have to be straight lines. So what this means is the speed of the kitty as it's moving away from Zargon isn't always the same. At this point, it could be moving at 10 meters per second, and at this point, it could be moving at 5 meters per second. So if we just do the distance traveled, let's say 100 kilometers, divided by the time taken, say 10 minutes, we are only getting the distance over the time. We're getting the average over all of the possible speeds that the cat could have been traveling at. So it is the average speed. Okay, let's apply this knowledge to a specific situation. Sadie the space clown. Now, I know a lot of you have a phobia of clouds, and I feel no shame. Endure the clown. Sadie the sadistic clown threw a pie at one of his counterparts. He's a nice guy. Only wanted to say hi, but Sadie was feeling fittingly sadistic for a sadistic clown and decided he was going to throw the pie at this so-called friend of him at 8 meters per second. Let's say the pie travels 5.5 meters. So what if someone asked you the question, for how long does the pie spend in the air before falling to its sticky, delicious, untimely death? Now I implore you, push you strongly to pause the video and have a go at solving it yourself before continuing to play the video. Had a go? Great! Well, if you plug in the values we had into the equation, we get, remember the equation is average speed equals distance traveled over time taken. So if we plug in these values, we get 8 meters per second if we assume that is the average speed of the pie. Distance travel, we have that as 5.5 meters over time taken. We don't know how long that takes. So if you rearrange the equation, we get x equals 5.5 meters divided by 8 meters per second. The units are getting a bit blobby, so I'll circle them so it's easier to follow along, which I believe gives us the value 5.5 divided by 8, that is 0.6875 is the time it takes for the pie to hit the ground. Thankfully, missing his good friend Bob. Well, I say good friend, but you know, he's a sadistic clown. Not many people want to be friends with a sadistic clown. Now, a tougher question which involves paying attention to units. What if there was a fugitive rollerblading cow? Okay, we have our fugitive rollerblading cow. Let's say they are trying to escape prison, because that's what fugitive rollerblading cows do in their spare time. Apparently, he's escaping from prison. We don't know what the cow did to get into prison, but we know it wasn't good. And we know it wasn't a maximum security prison because the door is wide open. Okay, so that is where our cow is coming from. And let's say it's been moving at 30 kilometers per hour. And it's been going at this rate for 10 minutes. How far has the cow traveled away from the prison 10 minutes later? First, we need to convert kilometers per hour to meters per second. How can we do this? Well, there are 1,000 meters in a kilometer, so we can multiply the numerator by 1,000. So let's get 30 kilometers over h. So we can get 30,000 meters divided by, and there are 60 minutes in an hour and 60 seconds in a minute, so we can multiply the denominator by 3,600, which is 60 times 60 seconds. And that simplifies to, if we cross out these two zeros and those two zeros, we get 50 over 6 meters per second. And that is equivalent to 8.33 meters per second. And that's a repeating decimal. We can just write it like that. Do not round. We'll try and keep the values as accurate as possible. And then to change the minutes to seconds, we'll just do 10 min times 60, because that's how many seconds there are in a minute, to get 600 seconds. So we have our two values that we can plug into the equation now. Remember, average speed equals distance over time. So if we plug those values in, we get 8.33 recurring meters per second equals x meters over 600 seconds. So if we simplify this, or if we rearrange this rather, we get 8.33 recurring times 600, which gives us 500 meters, which is exactly half a kilometer. So I'm sorry to say, Bertha, but you were too close to the prison. They could still smell your scent, and you're gonna have to go back. Poor cow. Maybe next time, Bertha. Okay, let's say we wanted to apply what we've just learned to a real-life, tangible, here, present, in real-life experiment. How would we describe an experiment to investigate the everyday motion of an object? The first easier way is to simply measure the time it takes for a toy car or a tennis ball or pizza to travel a certain distance. So we could get pizza rather. Nice big pepperoni pizza. Say this is 10 meters. See how long it takes for it to travel this distance at different speeds which we throw it at. So we could try throwing it at, let's say, 10 kilometers per hour or 20 kilometers per hour. And you just perhaps draw a distance time graph for either and compare and say, well, one situation it went a lot faster than other situations, and you could possibly look at the analysis of the experiment, and you can make it all very accurate and talk about how you can improve the results and whatnot. Or alternatively, especially for the Edexcel, I would suggest that you use this example. You should use the ticker tape one. Ticker tape is basically a strip of tape, and there's a machine that makes a dot on it every second. So each second it makes another dot, and the tape moves through the machine. So the tape is something that's being like pulled through. You can imagine it as rollers. I'm pretty sure there's more than one mechanism that this works, but I imagine it's one sort of something that makes a dent in a piece of paper, and it will make a dot on a piece of paper, and if it's moving at a constant rate through the rollers, it will have equivalent distances between each dot. But you can imagine if you pull it through really quickly, you will have larger gaps between each dot. Say this is 2x. In the same time period. So this is still 1 second. And if you did it at a much slower rate, then the dots would be much closer together, something like that. Call that half x. And this is still 1 second. So if we attached I'm tired of using cars as examples, let's attach a gigantic double chocolate fondant covered cream extravaganza with cherries. Yeah, that's more like it. We use one of these babies. We slide it down a ramp, and we want to measure how quickly it moves down. Well, we could attach this to the ticker tape at the top. And you can imagine if the cake was sliding down slowly, then the dots would be much closer together than if the cake slides down as if running away from a hungry me. This is because when there's a higher speed, there's a greater distance which is traveled in the same amount of time. Finally, one of my favorite topics in physics, acceleration. What is acceleration? Now, some of you probably already have a good idea of what acceleration is because of certain phrases in the vocabulary we have when we're talking about cars. Have you ever heard someone saying that a car goes from 0 to 60 kilometers per hour in Y number of seconds? Well, what they're saying, excuse me, what they're saying is the speed of the car changes from 0 kilometers per hour to 60 kilometers per hour in a set amount of time. By this definition, acceleration is a change of speed within a set amount of time. In other words, acceleration is the difference between two velocities, which is a vector quantity, and we'll move on to that in the next video, in part 2 of this video, I believe, giving us the equation. Acceleration equals change velocity over time taken. So if we had a velocity time graph, there'd be a couple of things that would make it different from a distance time graph. Now, let's have our velocity time graph. Velocity, which is measured in meters per second. This is time, which is measured in seconds. And let's just have our distance time graph, just for reference, to remind us of the differences. This is time, seconds. When the gradient of the graph is 0 on a velocity time graph, there's a big misconception that a lot of people have about distance time graph and velocity time graph. Here on a distance time graph, when the gradient is 0, it means there's no movement. It's still. On a velocity time graph, when the gradient equals 0, it's moving at a constant speed. Because it's, let's say this value is 5, for example, 5. It's moving at 5 meters per second, and it's not changing. it keeps moving at 5 meters per second. Therefore, it is at constant speed. It's still moving. A car could be chugging along, or a limo in this case, could be chugging along. Need a window. At a constant velocity of 5 meters per second. That doesn't mean that it's still. If the velocity increases as time goes on, so let's say this gets higher and higher, then that means the car has higher values for its velocity as time goes on, so therefore it must be accelerating. So this shows that it is accelerating. If the values for the velocity were decreasing over time, then it would be decelerating. It would be slowing down. Another thing is that the gradient of the velocity time graph is the acceleration. So the gradient is acceleration. Here, the gradient is the distance over time, and we know from the equation before that speed equals distance over time. So the gradient is the speed in a distance time graph. Yes. So if it is, let's have an example of this accelerating. Let's say we have a squirrel, a flying squirrel, and this increase, let's say this is 2, let's say this is 4, let's say this is 8. So if we say this is 2, that's not a very good graph, is it? Okay, let's try that again. 2, 4, 8, increasing values. Say 1, 2, 3. Okay, so every second the velocity is increasing by 2 meters per second. So it is moving at 2 meters. What was that? That's not 2. 2 meters per second per second. If we plug that into the equation there before, change in velocity over time taken for this period, change in velocity is 4 minus 2. So that is 2 over time taken. That's 1 second. So therefore, the velocity, change in velocity, which is in meters per second, over time taken. So that's 2 meters per second per second. So that's 2 meters per second squared. That is why the unit for acceleration is in meters per second. And the kind of cool thing about velocity time graphs is that you can find another cool thing using the area under the graph. This is time. This is velocity. If we had something simple like this, say 1, 2, 3, 4, let's say this is 5, and that's 10. So if we find the area under this graph, we can find the distance that the squirrel has traveled. So let's say, we all know, first of all, that the area of a triangle is half base. Can you see that? Okay, half base times height. So if we plug in the values for half base times height, the base of this triangle is 3. So it's half 3 times the height, which is 10. So we can do this without a calculator. We can just do half of 10, so that's easier to do in your head. That's 5. 5 times 3 is 15. So it's moving at 15 meters. That's the distance traveled as it accelerates from there to there in 3 seconds. It travels 15 meters. That's for part A. Right? For part B, it's a lot easier since it's a square, and we all know that the area of a square is length times width. So it would be 10. That would be this side here. This side here is 10 times this side here, which is 1. So you'd get 10 meters. So in total, 10 plus 15 equals 25. So the total distance traveled by the squirrel is 25 meters. Okay, so there are several forces that combine to make a resultant force on an object. For example, you, what I assume is a stationary object sitting in a chair, have an equal force U. Let's draw U. I'm assuming this is something the sort of what you're doing, sitting in a chair. Thinking physicsy thoughts. What's the symbol of a physicsy thing? Let's just draw an atom. Cliched, but what the heck. So you have equal forces acting on you. You have an equal force acting on you upwards as you do acting on you downwards, which is why you are not levitating above your seat and you're not being swallowed into the chair. The downward force pulling you down is gravity, and the upward force is being exerted by the chair on you. So the same force of gravity that Earth is pulling on you, you are pulling upwards on the Earth. So this is chair, the chair force, or the force between you and the chair, which is a weird thought to think you're pulling up on the Earth as much as it is pulling down on you. However, the reason why you don't see, huge massive changes in the way the Earth moves around because of people is because there's such a difference in the mass of the Earth, this big old thing, and the little us people. Just the ratio is so big that there isn't that much. We're not going to see that much of a change in Earth's orbit, for example, if someone is jumping on Earth, or if everyone on Earth jumped for that matter. Yes, so that is everything that we have for today. I hope you enjoyed the video. Please leave a like and a subscribe if you want more. If you get the video, you like the video, and you are sort of bored, I got this challenge that I'm thinking of getting down. For if anyone can give me a topic that they would like me to cover, then I will try to learn to solve this Rubik's Cube within 2 minutes and post it online. So if anyone at all, anywhere wants me to cover a topic that they would be interested in physics, it doesn't have to be IGCSE, it could be, something to do with particle physics, it could be something to do with chemistry, any topic that you want me to cover, and I will try and endeavor to make the video for you guys. If it's not too complicated, I'll see what I can do. I'll learn it, post a video, and then I will learn to solve this Rubik's Cube. Thanks so much for watching.